We're looking at polynomial functions today. So here are some features of polynomial functions. So a polynomial function is a function that has constants, variables, and exponents that are whole numbers. So they cannot be divided by a variable or have an infinite number of terms. So it does have to be a finite number of terms. Here's the standard form of a polynomial equation. So ax to the n plus bx to the n minus 1, so on and so forth, all the way to our constant g. So a, b, and c are coefficients. And the a sub n term is called the leading coefficient. That'd be right here. And n is the highest degree. Okay, so the next, we're going to see if these are polynomials or not. So go ahead and pause the video. This is a polynomial because the degrees are whole numbers, all whole numbers, and they have coefficients that are real numbers, and the degrees, there's a finite number of terms. Okay, the second one is a polynomial. Same thing. The third one is not because we have a fraction here. So when I divide, I'm going to end up with something like x to the 2/3, and that the fractional exponent is going to be bad. So something. How can we rewrite this one? This is x to the 1/2 power. So fractional exponents are not okay in polynomial functions. Okay, E is yes. Technically, this is x to the 0 power, or 8x to the 0 power. The third one is a yes. It's just written in factored form. So when I multiply, I'm going to get negative 2x to the 4th. Oh, just kidding. You have to multiply that first. Okay. So when I multiply x times x, you get x squared minus 2x plus 1 times negative 2x cubed. Now I can multiply that in, giving me negative 2x to the 5th plus 4x to the 4th minus 2x cubed. And now your polynomial looks like a regular polynomial. All right, so the degree of the first, of a, is, so the degree n is equal to 3, and the leading term a is equal to 5. The second, it's out of order, but we're going to look at the highest degree. So n is equal to 4, and the leading term a is equal to negative 3. So a is equal to negative 3. We don't have to worry about those. This one, the degree is 0, and the leading term is 8. Lastly, I have my degree is equal to 5, and the leading term is equal to negative 2. Okay? So when we sketch polynomials, they are smooth. So they look more like this. Smooth lines, not with corners or cusps or holes. So a corner or a cusp or a hole. Okay. Or also a hole could look like this, just a spot taken out of the graph, like that. So still connecting, but a spot taken out of the graph. So make sure they're nice and smooth like the left and not like the right. All right, so zeros of polynomials are called roots, x-intercepts, and solutions. They're so important that they have 4 names, basically. So zeros, roots, x-intercepts, and solutions. How many real roots can the following have? So if you have a second degree polynomial like a quadratic, how many real roots can it have? Let's have some examples. I have 2 real roots. I have 1 real root. Or I can have no real roots. A third degree polynomial can have, let's see, it can cross 3 times, it could cross 2 times, and it can cross 1 time. Can it cross 0 times? No. Okay, so for the polynomial of degree n, the function of degree n, so like this one would be x squared plus something, something, something. So its degree is 2. So at most, the polynomial can have 2 real roots, whereas this one, x cubed plus something, at most it can have 3 real roots. So we say at most it can have n real roots, so matching its degree. Okay, and then the function at most has n minus 1, so 1 less of its degree, relative extrema. So a quadratic has 1 relative minimum or 1 relative maximum, which is less than one unit less than its degree. It's 1 unit less than its degree. A third degree polynomial can have 2 relative extrema or less. Okay. All right. So the next part. For zeros, if you have repeated factors like x minus r to the k value, or let's just make an example, like x minus 2 squared is equal to y, then let's just move this. Okay, so if k is odd, so y is equal to x minus 1 to the third power, then the graph will cross the x-axis. So if your degree is odd on the actual root itself, then the graph will cross the x-axis. I know you talked about this in Math 3. Okay, so if I have an example like x minus 1 squared, then if the degree is even, the polynomial will bounce off the axis. Okay, so we're just going to list the real roots really quick. I can see using zero product property that x plus 3 is equal to 0 and x minus 5 is equal to 0. So x can equal negative 3 and x can equal 5. These are my roots. This has a multiplicity of, I just write an m, a multiplicity of 4, which is even. And this has a multiplicity of 3, its degree, which is odd. Okay, so the 4 will make the graph bounce off the root, and the odd multiplicity will make it cross. The leading coefficient, a, is equal to 1, okay? And we're going to look at what that means right now. So I'm just going to graph these in. 1, 2, 3. 1, 2, 3, 4, 5. And put some dots. We'll figure out which direction those go in a second. Okay. Okay. Another test to be able to sketch our graph is our leading coefficient test. So we say that eventually the graph will rise to infinity or fall to negative infinity on either end. So when the degree of the polynomial is odd and the coefficient is even, or sorry, is positive, so your a value is positive. So this would be like when your leading term is like y is equal to 4 times x to the third power plus some more terms. The graph will fall on the left and rise on the right. These are backwards. So rise on the right and fall on the left, we write this like this. As x goes to infinity, y goes to infinity. This one is as x goes to negative infinity, y falls to negative infinity, or approaches. Okay? Next, if the leading coefficient is, so if the polynomial is odd and the leading coefficient is negative, the graph will rise and fall. So on the left, the graph rises. On the right, the graph falls. So on the right, we write as x goes to infinity. That's fancy words for on the right. The y value goes to negative infinity. On the left, as x goes to negative infinity, that means on the left, y goes to positive infinity. All right, when the degree of the polynomial is even and the leading coefficient is positive, like y is equal to 5x to the fourth power plus some terms, the graph is going to rise on the left and rise on the right. So like this. So we write as x goes to infinity, y goes to infinity. And as x goes to infinity, y goes to infinity. If the degree is negative, the graph will fall and fall. Okay, so like y is equal to negative 4x to the fourth power. Okay, we will fall and fall. Think like a parabola, just with more going on in the middle. So as x goes to infinity, y is going to go to negative infinity. And as x goes to negative infinity, which just means on the left, y falls to negative infinity. All right, so we're going to do 3 examples. Oh, we're going to go back to this other example. So it says that we want to check out our leading coefficient. So our leading coefficient A is equal to 1, which is positive or negative. It's positive. And the degree is equal to, what you got to do when it's in factored form is add the degrees, so the multiplicities. So I have 4 plus 3 gives me 7. So, and that means that that's odd. So going back to my leading coefficient test, I have odd and positive. So the graph is going to rise and fall. Okay. So I'm going to sketch this in as so. This is going to, on the right, on the last 0, we're going to rise. And on the left, we're going to fall. When x is equal to negative 3, the root bounces, so it touches the x-axis and bounces off. And on the left, it goes through. And it all matches up, so we're good to go. All right, next. Write the equation and sketch the third degree. So third degree polynomial with zeros at x equals 3, -1, and 2, and a positive leading coefficient. So if I have zeros, I'm writing this thing in factored form. So I'm going to write x minus my root 1 times x minus my root 2 times x minus my root 3, all times my leading coefficient. So I'm going to just choose a value for a because it wasn't specific this time. Minus 3, x plus 1 times x minus 2. Okay, and we're going to sketch this really quick. So I have roots at 3, -1, and 2. Those are tight together. And I have a leading my n is equal to 3, which is odd, and my leading coefficient is 7, which is positive. So my arms are going to rise and fall, just like my last example. And each one of these roots has a multiplicity of 1, so we're going to go through on each one. Okay, we're going to leave this one for our warm-up. The third one, write the equation of a third degree polynomial function, again, that has zeros at -1, -2, -1, and 2, and includes the point 0.04. Okay, so again, in factored form, a times x plus 2 times x plus 1 times x minus 2. So the opposite of each of these roots. And it goes through the point 0.04. So how do I find my exact a value? Well, I'm going to plug in my point 0.04. So x is my 0 and y is my 4. So I'm plugging 4 is equal to a times 0 plus 2 times 0 plus 1 times 0 minus 2. So this is just like as if you're finding the a value of a parabola. Okay, so 4 is equal to a times 2 times 1 times -2. So 4 is equal to -4a divided by 4. A is equal to -1. So my equation is y is equal to -x plus 2 times x plus 1 times x minus 2. And that is all for today. We have another video coming tomorrow. Bye.